Well, in the previous video, we said that we can also have ions that can be considered aromatic. And we got a couple of examples. And one of them was the anion. This one here on the left. So this is the anion of the cyclopentadiene with a negative charge on this carbon atom. And then we have the cycloheptatrienyl cation. So we have a positive charge on one of the carbon atoms. So in the next slide, I want to compare three structures. So here we have on the left the cyclopentadienyl anion. In the center we have plain benzene, neutral. And then on the right, I have the cycloheptatrienyl cation. And there you can see on top, I have the drawing of the orbitals, right? And so there you can see that in the structure on the left, I have that each one of the carbon atoms is making a contribution of one electron, one electron, one electron, one electron. But there is one of the carbon atoms that has 2 electrons in the orbital. That's why it's negatively charged. And there you can see that the total number of pi electrons is 6. And that's why this is aromatic. Then the next one is benzene. Here, the six carbon atoms, the 6p orbitals, they have 1 electron each. And that's how we end up again. We will end up again with 6 pi electrons. And then in the last one, we have 6 of the carbon atoms. They have 1 electron each. 1, 2, 3, 4, 5, 6. And then, attention, attention. So there is one particular p orbital that is vacant. And because it's vacant, so that's why our total is still 6. And that's how we end up with 6 pi electrons, which will make it aromatic. Let me insert one slide here to discuss the writing of additional resonance structures for these guys. And so, see, when you have the structure of the cyclopentadienyl anion, how many additional resonance structures can you write? Well, you can bring this pair of electrons here, that one there, that one there. So one additional structure will look like this. I will have my double bond here and here. And now, oops, sorry. I made a mistake here. Made a mistake there. So then this guy here, I am localizing that pair of electrons there. So that means that my bonds now are here, here, and now I have the lone pair of electrons there, right? Then what else can I do? Then I can bring the pair of electrons here, there now, then this one here, and now I localize this one here. So there you have a new structure in which you have double bond here, here, and now this is the carbon atom with a lone pair, etc., etc. I can keep repeating the same. And then you get the idea that you can see that at any moment, one of the carbon atoms of the cyclopentadiene will become negatively charged. And so when I do this one here, now this is my carbon atom with the negative charge. And I have one more, right? And just one more. So that one more will be, I can bring this here, and I localize this one there, right? And so there you go. Now that one is the negative, and then those two are pi bonds in both. All right, so there you can see that that is the reason why when we have the electrostatic potential map for a compound like this, actually you will see that each one of the carbon atoms, it has just about the same electronic density. And so we can have like a partial double bond in each one of the pairs of carbon atoms, and all the carbon atoms will exhibit a delta minus, right? Delta minus, all the way around, right? That is very nicely represented when you look at the electrostatic potential map. You will see that each one of the carbon atoms, it has a partial negative charge. Then in the next slide, what do we have here? So we have the aromaticity of the cyclopentadienyl derivatives. So there are three things that we can do with the cyclopentadiene. One thing is that I could remove just one hydrogen atom. If I remove just one hydrogen atom, I need to use the fish hook error. One electron goes with the hydrogen, the other electron stays on the carbon. And what we obtain out of that will be a cyclopentadienyl radical, right? There is no charge here. This is a radical. Another thing that we can do is that I can remove altogether, I can remove a hydride. How can I remove a hydride? I will need to use an electrophile for that. So if I have an electrophilic species, positively charged, so then now I can get one of the hydrogen atoms will go with a pair of electrons to get attached to the electrophile. So I am removing an H minus, and that's how I am forming a cyclopentadienyl cation. When I remove a hydrogen atom with a pair of electrons, so what is left behind, it will be a cation. Right, so that is one other thing that I can do. We just discussed that this guy here is aromatic, right? I'm sorry, that guy is not aromatic. It's not aromatic because here I will have a total of 4 pi electrons, right? 4 pi electrons. So this is not aromatic. The anion is aromatic. And then the other thing that I can do is the removal of a proton, right? If I remove a proton, in that case, what I will leave behind, it will be the anion, and the anion has 6 pi electrons. So this guy here has 6 pi electrons, and that's why we say that is aromatic, right? So this guy is aromatic. That is the one we were discussing before. How can you remove a proton? What do you need in order to remove just one proton? Well, obviously you need a base, right? We have learned that in organic 1, right? So if I have a base with a pair of electrons, and so I can grab one proton, and then in that way, what I leave behind will be the anion there, right? How strong should be that base? Well, the strength of the base will depend on the stability of the anion that I am obtaining, right? So because I am obtaining an anion that is relatively stable, right, because it's aromatic, it turned out that the strength of the base, it will not have to be so fantastic. So it will be enough to use a base like, I could say even hydroxide, it could be enough. And maybe we can get a little stronger than hydroxide because of the pK value of, a little stronger than hydroxide. So you can use like a methoxy group, that will be good enough. And that will allow you to abstract the proton. Okay, so then now we can look at in more detail the formation of the cycloheptatrianyl cation. How can you do that? As I said before, you can use an electrophile in order to remove a hydride. And by doing that, and so in this case, McMurray is illustrating that by using bromine, Br2, and then you get the formation of the cation with a bromide, a Br minus as a counterion, and then in the removal of the hydride, you could have formed HBr, right? So there you go. Let me just highlight here in this drawing, let me highlight that each one of the carbon atoms has one electron, one, one, and one. And so there you have 6 electrons. And notice that the carbon atom that is closer to us, this one here, is vacant, right? So there is no dot in that one. So that is the reason why you will have the cation. And then when you have the representation of the electrostatic potential map, and then you can see that all the carbon atoms, they will have roughly the same electron density. So that's why it looks so homogeneous. So here again is one case where we can write down a whole bunch of resonance structures for this. I will write down just a couple additional resonance structures. So what can I do here? So I'll write down just one more. What can I do here? I can bring a pair of electrons here. So then now I don't touch that. I don't touch that. So then now this is going to be my positive charge. And then here what? I can bring this other pair of electrons there. And then now this is going to be the positive. And then I will have double bond here, here, and there, right? Etc., etc. And so that's how you can get 7 resonance structures, right? 7 resonance structures. Aromaticity with heterocyclic structures. Heterocyclic. When we have that prefix hetero, it means that you may have elements different than carbon. You can have nitrogen, sulfur, oxygen, phosphorus, and so there is a great variety of other elements that will be suitable for having heterocyclic structures. There are 3 structures that we will study in some detail. One of them will be pyridine, the other one is pyrrole, and then the third one is imidazole. In the case of pyridine, pyridine is very, very similar to benzene. You have a 6-member ring. You have 3 pairs of double bonds. The only difference is that one of the elements of this ring of 6 is not a carbon, but is a nitrogen. And we will see that that nitrogen still has a pair of electrons that doesn't participate of the pi system. And then the other one that we will see in detail is pyrrole. Pyrrole looks like this. The nitrogen has a lone pair of electrons and a hydrogen atom attached to it. And we have 2 pairs of carbon-carbon double bonds. So in the next mini video, we will examine this in greater detail.